We're now going to see if we can find the inverse of a matrix. Recall that M sub M comma N R, where R here is a ring. This forms a multiplicative group. It also forms an additive group. M sub M cross N of F, where F here is a field, forms a vector space over this field F, and it forms a non-commutative ring. The identity matrix. Let I be the identity matrix. It is a matrix whose ith jth entry is delta sub ij, where delta sub ij, the Kronecker delta function, is just equal to 1 if I is equal to j, and 0 where I is equal to 1 up to n, and j is equal to 1 up to n. A non-singular matrix. Let A be a M by N matrix. Then A is said to be non-singular if there exists some matrix B such that A times B is equal to the identity. We note that that it can be shown that if a matrix has an inverse, then it must be a square matrix. We call the matrix B the inverse of the matrix A, and we denote this by A with a superscript of -1. So, why do we care about inverse matrices? Well, A times, suppose A is a coefficient matrix, and X is the variable matrix, and it's equal to some non-homogeneous matrix B. Then I can multiply both sides of my equation by A inverse if A inverse exists. Well, A times A inverse is just equal to identity element. Identity element times the matrix X is just the matrix X. And so X is equal to A inverse times B. So if I can find an inverse, then to find the solution, all I have to do is multiply that non-homogeneous part by the inverse of the coefficient matrix, and that will give me the solution to my system. Note that in general, matrix multiplication is not commutative. So A times B is usually not equal to B times A. So that's why I'm a little bit careful when I write multiplication that I write in the correct order. They don't change anything. Another way of thinking about this is that a technique to determine how to find an inverse for a matrix will be as follows. Suppose I have the system of equations, A matrix, coefficient matrix A times the variable matrix X is equal to the identity matrix. Then, if I multiply both sides of my equation by A inverse, I have that the identity times the matrix X is just equal to the inverse matrix of A. So, seeing this symbolically, I have that if I start out with a augmented matrix where A is on the left side of the matrix and the identity on the right-hand side, then if I perform elementary row operations to change the left-hand side to identity, the right-hand side becomes the inverse matrix. And so that's a technique to determine the inverses. Why would we want to use matrices? If I had the following situation, suppose I wanted to solve the equation, system of simultaneous linear equations, ax equal b1. Then I want to solve the equation ax equal b2. Then I want to solve the equation ax equal b3, etc. Well, it turns out that then the variable matrix x is equal to A inverse times B1. For this equation, system of linear equations, I get x is equal to A inverse B2. For this one, I get x is equal to A inverse B3. So if I know what A inverse is, then all I have to do is multiply by the b's to get the solutions. So if you happen to have a whole bunch of equations where the coefficient matrices are the same and the non-homogeneous matrices are not equal, are not the same, then to solve these, you just keep multiplying by the inverse of your coefficient matrix. So, if you have, well, there's a lot of work to find the inverse matrix, but, if you have to do it 3 or 4 times, then it's certainly much cheaper, much more efficient to find the inverse matrix first, rather than having to solve these equations over and over again. Page 598, find the inverse of each matrix if possible. So let's rewrite this as an augmented matrix, where the right-hand side of my matrix is the identity, using the idea that we've had from before about pivoting, about writing it in this case, reduced row echelon form. Let's pivot. Let's multiply. Let's take the second row, subtract from it the 2 times the first row to get me a new second row. So if I do that, I get 1 minus 2, 1, 0. I'll multiply by -2 and add to the second one. So 2 minus 2 is 0. -5 minus -2 times -1, -5 minus 4 plus 4 is a -1. -2 plus 0, -2. 1 minus 0 is 1. Let's take the second row, multiply by -1 to give me a new second row. Once I've gotten the new second row, let's take the first row, add to it twice the second row to get me a new first row. Okay, so this is equal to, multiply the second row by -1, so 0, 1, 2, -1. Multiply by 2 and add to the first row. So 0 plus 1, 2 plus 4 plus 1, 5, negative. So 2 times -1 is -2 plus 0 is -2. Therefore, I get that is okay, good. So the inverse to our matrix 1, 2, -2, -5, I get that the inverse of this is equal to 5, 2, -2, -1. That is the inverse of my matrix. Okay. Let me do problem number 32. Use matrix inversion to solve each system of equations. Note that several systems have the same coefficient matrix. So it would be easier if uh, I'd done several equations with the same coefficient matrix. I'm just going to do one of them, but notice that once you have done all the work of finding the inverse matrix, to find the solution is fairly straightforward and fast. Okay, so first off, here, let me get another page. First off here, let me rewrite this, so interchange the first and third rows. So it looks nicer. Yeah, just do it, squeeze. So 1x, no y, 1z equals -2. 2x, 3y, no z is 1, minus 2x, 1y, minus 3z equals 5. Okay, so let's pivot. So I want to eliminate this 2 here, and so I'll take R2, subtract from it twice R1 to get me a new R2. For this, I'll want to eliminate the -2, so I'll take the third row, add to it twice the first row to give me a new third row. Okay, so, whoa, wait, I'm sorry. I always made a big mistake there. And I want to figure out the inverse. Notice that's the only difference between what I had done previously and what I'm doing right now. Is on the right-hand side, I put the identity rather than the non-homogeneous part. Oh, ooh. I interchange first and third rows. So I better do that. Oh. Actually, let's just do that first. So 1, 0, 0, 0, 0, 1, 1, 0. Okay, so I have a 1, 0, 1. Haven't done anything there. 0, 0, 1. Okay. Let's take the second. Subtract twice times the first. Okay, so 2 minus 2 is 0. 3 minus 0 is 3. 0 minus 2 is -2. 0 minus 0 is 0. 1 minus 0 is still 1. 0 minus 2 is a -2. Okay. Lastly, 2 times the first row. So 2 minus 2 is 0. 0 plus 1 is 1. 2 minus 3 is negative 1. 0 plus 1 is 1. 0 plus 0 is 0. 2 plus 0 is 2. Let's interchange row 2 and row 3. So that my pivot will be here. I want to make this 0. And so I'll take the third row and I'll subtract 3 times the second row to give me a new third row. Okay, let's do that. Don't do anything with the first one. 1, 0, 1, 0, 0, 1. So I interchange the second and third row, so I get 0, 1, minus 1, 1, 0, 2. I'll now multiply this second row by negative 3, add to the third one. So 0 plus 0, 0. 3 minus 3, 0. 3 plus 2 is 1. 3 minus 2 is 1. Okay, good. 0 minus 3, negative 3. Wait 1 second. Let me just check if I multiply. I multiplied this by negative 3. Yes. 0 plus 1, 1. Minus 6 plus 2, minus 2 is minus 8. Okay. And so I want to make each of these 0 above here. So I'll take R1, subtract R3 to give me a new R1. I'll take R2, add R3 to give me a new R2. So I get finally 1 plus 0 is 1. 0 plus 0 is 0. 1 minus 1 is 0. 0 minus 3 is negative 3. 0 plus 1 is 1. 1 minus 8 is minus 7. Add. Wait, I subtracted. Oh, darn, I subtracted. I subtracted. So this would be 0 plus 3. 0 minus 1. 1 plus 8 is 9. Okay, now let's do the second. And so now I'm going to add 0 plus 0 is 0. 1 plus 0 is 1. 1 minus 1 is 0. 1 minus 3 is negative 2. 0 plus 1 is 1. 2 minus 8 is negative 6. And we have 0, 0, 1, minus 3, 1, minus 8.
Does my room look really...
Okay. And so, now that means that the inverse matrix, the coefficient matrix, well, I didn't call it anything, but let's say that it's called A. So it says that A inverse is 3, negative 2, negative 3, negative 1, 1, 1, 9, negative 6, negative 8. Okay, so now let's determine my solution. And so I have that X, my solution. Let's just see what the X's were called, X, Y, and Z. So X, Y, Z is equal to A inverse, -3, -2, -3, -1, 1, 1, 9, -6, -8, times the non-homogeneous part. And the non-homogeneous part was -2, 1, 5. Okay, so let's see what that gives us. Okay. 6 minus 1, 5 plus 45 is 50. So X is 50. Just multiply this out. 4 plus 1 is 5, minus 30 is -25. 6 plus 1 is 7, minus 40, -33. And so you get that X is 50, X is 50, Y is -25, and Z is -33. And that is your answer. Let me do problem number 43. Show that a squared equals 0. Okay, so what we're noticing here, well, let's do this. So let's look at a squared. So a squared is equal to -1, 1, -1, 1 squared. So this is equal to -1, 1, -1, 1 times -1, -1, 1, 1. So let's multiply this out. So this is equal to -1 times -1 is 1. Minus 1 times 1 is -1. So 1 minus 1 is 0. 1 minus 1 is 0. -1 plus 1 is 0. -1 plus 1 is 0. So what we have shown is we've shown that a squared is 0, yet a is not 0. So I've squared a non-zero number and got 0. So note in general, and this is because the matrix was not invertible. And so this is because A was singular. Well, this can only happen if A were singular. So this can only happen if A were singular. meaning that it doesn't have an inverse. So notice that what that means is that you don't even have cancellation. So what this means is that in general, the zero factor property does not work. Oops. Zero factor property does not hold for matrices. So A times B equaling 0, this does not necessarily imply that A is 0 or B is 0. As we've seen, I've shown that A times A equaling 0 doesn't mean that A is equal to 0 or A equals 0. So I could have that I multiply, maybe I have the multiple of two matrices is 0. I can't